Can everybody see the presentation?
Yes.
Good, good. So I'm gonna do a quick introduction into a parameter estimation in COPASI. So what is it all about? Parameter estimation is a form of optimization. In optimization, we have some kind of objective function that we want to maximize or minimize depending on what we want to do. And note that if you maximize, it's just minus. If you minimize the inverse of the function, then it's a minimization problem. So in general, I'm going to talk about, when I talk about optimization, it's minimization. And we want to minimize a function, arbitrary function, given some parameters, which are within certain bounds. And for that, we want to find the smallest value of the function. Down here, if we look at the simple function, the minimum is somewhere around 7. So how do we do that in general? In COPASI, we have a function. We start with an initial guess of our parameters within the range provided. We evaluate the function, which can be a steady state or time course, or it can be any kind of function method to provide the values for the function. Then we say whether this solution is good enough, whatever that means. And if it's not good enough, which in most cases it will be, then we determine new values and follow with this cycle till either the function is good enough or we decided we are running out of time, we want to stop. So there are different criteria. So how does that now all work in COPASI? We have different methods. Some are gradient based, like steepest descent, Newton and quasi-Newton, or Levenbeck-Marquardt. They're actually more. Then we have some other ones which are direct searches, Hook, Jeeves, Nelder-Mead, or Brandt's Praxis algorithm. And then we have stochastics methods, random search, simulated annealing, particle swarm, evolutionist strategies, generic. Those stochastic methods basically mostly the bottom four deal with the population, which evolves over time, and the upper one are basically a random search under certain criterion. Stochastic methods tend to be better if you have multiple minima to find the global minima, whereas gradient-based are very good in approaching the local minima from your current situation. Direct messages have benefits of both of them. There are different messages in COPASI because of problems, your situation. One or the other approach might be the best. So how does this optimization and all these algorithms now relate to parameter estimation? In parameter estimation, we basically have the function which we want to minimize defined to by experimental data. So we have observed data. It could be a time course, it could be a steady state. And now we do a simulation. Either we calculate a time course or a steady state and determine the distance between the measured values and our simulated values at this point in time. So here we have a very simple straight down projection, which is you can find at the bottom here. So we want to find the minimum of our experimental set x minus the value of x based on our parameter k. And this is a problem we want to minimize. With this in the background, I'm going to switch now to COPASI. and gonna go through some simple examples on how this works. I will share these examples on our Google Drive after the presentation, so you can go through it on your own time if you like. So the first one, I want to look at a situation where we have local fits. Question, is this big? Oh, sorry, that's not the one. Is this big enough for you to see the font for COPASI? I can increase. I don't hear any objections, so I stay with this. So we have a very simple model. 2 species, 4 reactions, only mass actions. I have constant influx and conversion and outflux. It's a very simple model, and I have experimental data for it. Let me see if I can share that. So this is the data. I created, there is the actual value and the observed values. We will fit to the observed values, which basically have some noise added to the experimental value. So now we go to the parameter estimation task. And first thing I do is to look at the experimental data. And what I'm doing, so let me look, let me just, for the sake of it, show you how it works. I add an experiment, wrong folder, local minima, local data. COPASI looks at the file, figures out the column names. This is a time course. I know about the data. COPASI figured out that it's tab separated and has 52 rows. And first thing is, you notice that for the time column, COPASI said, oh, that is time. It tries to figure that out automatically. If something is called some version of time, it will do that. And let's just fit the last column. This is dependent data, so that means it's going to be simulated, and that is the value of transient concentration of our species Y. Okay, that's how you define the experimental value. You can have multiple files, you can have multiple experiments in the same file, and you can mix steady state and time course simulation. So let's see. Yeah, it's all there. The next thing we do is we define our parameter which we want to estimate. In this case, these are basically all reaction parameters and the initial values of X and Y. So I have created already some plots for this, especially the parameter estimation results and the progress of fit. But if you don't have them, we have the output assistant, which allows you to look at the parameter estimation result in one plot, in plot per experiments, or plot per value you are fitting. So let's just run this and see what happens. So I choose Leeuwenberg-Marquardt, which looks is pretty fixed, fast, but gets stuck in a local minima. So here is a straight line. What you would observe if you move it up or down, the error will be worse. If you just look at the errors that follows a pattern, always if you see a pattern in an error, means you don't have a good fit. Let's just run this another time. This time we have another solution. Again, local minima where we have the line. The simulation is pretty good, but it doesn't capture the oscillation we are having. So I claimed that stochastic algorithms are, or population-based algorithms are better in finding global minima. Let's see if my claim is true. I use my favorite algorithm, which is particle swarm, and run it. We can look at the progress of fit. Runs pretty fast. Based on my experience, it's stuck in a local minima. I know what the best value is if it gets out. It's getting better. Let's look at the parameter estimation. It found it, but at the very end. So here we see the differences between global and different global minima and local different minima, and we also see the benefits of stochastic population-based algorithms finding a global minima versus Leeuwenberg-Marquardt, which tends to find the local minima. One thing I like to add here is, let's go back to Leeuwenberg-Marquardt. You run it. It's very fast. That's a benefit. But the results are local. There is a trick if you have oscillations to improve this behavior. So if we look, let's say up to 40, that's how many time points? Let's say about 22 time points. That's the first oscillation. Let's limit our experimental data to that. Instead of going to row 52, let's just go to row, let's say 24. So I told COPASI to ignore the rest of the experimental data. And now I run it. And we see Leeuwenberg-Marquardt found the oscillation quite nicely. So what we now do is we change, since we are close to the solution for the oscillation, we select all these values and say the start value, instead of randomized, it's going to be the current solution. I need to untick that. Now I add back all the experimental data. I remember it was 52 rows. Oh, I put too much in. COPASI says that's not correct. 52. If I do 53, it's not correct. So it verifies that you do not go past the limit of your experiment. Okay, I run it, and yeah, it still doesn't get it good enough. It's a damped solution, but better than everything we had without doing it this way.